Dr. Joe Liebes, who's the chair of the Department of Civil Engineering here at the University of Minnesota. And again, we're very appreciative of the support and the collaboration that the university extends to MTS over the last decade or more. I'm sure you'll hear more about the facility from both Joe and Art Shultz and Paul through the course of the day. So I won't talk too much about the facility, but you know, we're really glad to be associated with this venue and your support. Thanks, Joe.
Well, welcome, and Ray, thank you so much. The department has really had over the years very close cooperation with MTS that we're very appreciative and very proud of. I thought I'd just take a few minutes, of course, to welcome you. Most of you, I believe, are from out of state, so I'll give you a little snapshot about the university, about the college, and about the department. The university was founded before the state of Minnesota was established. We have 5 campuses. The Twin Cities campus does have 2 locations, Minneapolis and St. Paul. Engineering, the sciences are on the Minneapolis campus. And if I could say, although it's not called that, the Ag School is St. Paul. The college is somewhat unique for a major research university in that we have mathematics, physical sciences and engineering together. And we think that's a huge advantage with interdisciplinary work, collaboration that takes place, we'd like to say, seamlessly. In terms of the department, we have a diverse faculty. I brag that half of our faculty have one of their degrees from an international institution from outside the United States. We're a little heavy on the professor side, but we have 8 outstanding assistant professors doing very exciting work. Of course, being at a major research university, research is a very important function of the department, along with teaching and outreach service. Our department is civil, environmental, and geoengineering. We have 3 undergraduate degree programs within the department, as our name implies. Environmental, somewhat new, although certainly our department being one of civil engineering, environmental research teaching has been a very active component from the start. And geoengineering has a long history dating back to the School of Mines that was at the University of Minnesota. Okay, I am very fond of our building. It is underground, 7 stories underground. And I'm very proud of our laboratories. So I'm a lab guy, and you see one of our outstanding facilities here, the MAST Lab. We also have the Colombo Structural Engineering Laboratory that makes up the core of our building. That's that central area here. So what I'm showing is a cross-section of our building where the first 3 floors are an open cut. 2 shafts were driven and a mine space is created to form the 6th and 7th floors. So going through the labs, so-called WAVES lab that features a laser Doppler vibrometer where we can measure displacements of sub-micron level. The rock mechanics lab where I live, which houses 4 MTS load frames. And again, we have a long cooperation with MTS in utilizing closed-loop servohydraulic testing for looking at how brittle materials behave beyond the peak load, and these other labs. So one last thing about the department, if you have time, visit our website. We put together a collection of contributions from faculty and students in the form of this, what we call coffee table book, and it is available online to view. And certainly one of the features of this book is MAST Laboratory. So I'm anxious to hear from Art about all the exciting things that have gone on and will go on with your cooperation. So again, thank you for being here, and of course, thank you very much, MTS, for helping us put on this, this workshop. Ray.
Well, I'd like to introduce our next speaker. We have Dr. Art Shultz from the University of Minnesota and Paul Bergson. I think they'll give an overview of the MAST facility here so that you can understand both the capabilities and some of the system specifications and performance. You know, one of the things that is available to any of you is potentially to use this facility in some contract capacity. So, you know, when it comes to large-scale testing, there are very few facilities of this capability around the world. And so, you know, I would encourage if any of you have some ideas of component testing to contact these gentlemen, and they may be able to, you know, help you in the future as well. But learn more about it through Art and Paul.
Thank you very much, Ray. It's really a pleasure to be addressing you guys here today. Thank you, Joe, for such a nice presentation and to introduce the department. Paul and I are going to briefly introduce the MAST Lab, or I hope it's briefly, and as part of this we will show at the end a few videos of projects that have gone on here in the MAST Laboratory. The MAST Laboratory was developed as part of the National Science Foundation program on the network of earthquake engineering simulation. This program went on for 15 years, and the MAST Lab was very active over those 15 years. This program has ended, has sunset, as NSF says, uses the terminology. But the lab still continues, and we're trying to expand ways in which we can use the lab. It is the largest facility of its kind in the world, and that is, to a great extent, a credit to MTS for being able to help us realize the vision of what we could do here in the MAST Laboratory. It features a 6-degree of freedom controller that allows seamless multi-directional loading, which is essential for what we wanted to do. And it also has a very large payload capacity, as you can see, and very large force and displacement capacities for testing. The MAST Laboratory was initially envisioned so that we could do quasi-static cyclic testing, as is common in earthquake engineering, but also with the hope of being able to expand the functionality to ramp and hold hybrid testing, which is the subject of this workshop. Talk very briefly about quasi-static cyclic testing. The advantages for testing this way are that you can test real structural elements as opposed to material samples. You can observe failure as it evolves and gain insight into specimen behavior. But it does have limitations. You can't simulate dynamic effects. Can't simulate a particular type of hazard. If it's a seismic hazard, that would be the specific earthquake. And if the specimen is part of a larger structure, then you have separated it from the structure and you have violated boundary conditions. You replace them with idealizations that may not be very good, and quite often the size of the specimen is limited. Hybrid simulation, this is a method that, you know, in different phases or forms has been around for some time. The idea is to begin with the excitation or the input loading for the hazard. If it's an earthquake hazard, it would be a ground motion. And instead of going directly to a test specimen, you use that hazard or that ground motion to load a model, a virtual model of a structural system in its entirety. It could be the entire structure, it could be the structure and the foundation, it could be the structure, the foundation, and soils over a larger area. And you calculate an increment in displacements at the degrees of freedom of interest. Then you take those displacements and you impose them on a physical test specimen of a portion of the structure. Now, to be able to do this, you have to load all of the ends of the specimen where it has been virtually removed from the structural system. In other words, the forces at the boundaries. Then you measure the restoring force and the displacement feedback, and that goes back into your structural model, and you use that to update the model itself, the finite element model. And then you go back and recalculate the next increment in loading. There are some limitations to the system. It's sensitive to small experimental and numerical errors, and so far you've been limited to lump mass systems. If you're not doing real-time hybrid simulation, then you have problems with creep and relaxation. If you load and then stop while you are holding the load, the specimen, most materials will creep. And in addition to that, you're not going to get the dynamic effects from inertial loading. That's why real-time or fast hybrid simulation has become very popular for earthquake engineering and other loading regimes. Here in the MAST laboratory, I'm not going to fool you. We can only do slow hybrid simulation. In other words, the loading has to be applied slowly, and that's for a number of different reasons having to do with how the system was built. However, it does give us the opportunity to address some of the other problems. So some of the things that we can address is loading in multiple directions, okay? Addressing forces at boundary conditions where you remove a structural member from the larger system. Implementing gravity loading, implementing vertical loading if it's not constant, bracing the specimen so that it doesn't become unstable during testing, addressing size effects by simply going to the full scale or near full scale. We can't, of course, address the dynamic effects. So what is the MAST? Well, the MAST is a series of components. You have the physical components that you see out here, as well as a controller. The physical components include a very large crosshead and a series of actuators. So there's 4 horizontal actuators, 2 in each of the horizontal directions. They're each 440 kips in load capacity and plus or minus 16 inches in stroke. They have U-joint swivels that can move plus or minus 25 degrees. We also have 4 vertical actuators that serve to support the crosshead. These are each 330,000 pounds and have a stroke of plus or minus 20 inches. Instead of having U-joint swivels, they have hydrostatic bearings, which you can see here. You can see part of it. It's the shiny ball at the top and bottom of each of the actuators. During operation, oil is continuously if you wish, emitted around these swivels so as to reduce friction. And it reduces friction to the point where it's essentially negligible. That's very important because the vertical loads can be very high, and if we had a traditional U-joint swivel, we would be having to overcome the friction first before we can load the specimen. In addition to that, we have 4 actuators that we refer to as ancillary actuators. They're not shown here in the photograph, or they're not placed out in the payload itself. These actuators we use for purposes of providing additional loading or support of specimens. We can attach them to the specimen and to the reaction walls, or we can attach them to the specimen and to the reaction floor, depending on what additional forces or supports we need. Everything is powered by a 190 gallon per minute pump. The concept behind this 6 degree of freedom testing system is that we subdivide space into 3 orthogonal directions, X, Y, and Z, where X and Y are the 2 horizontal directions. I'll refer to one as lateral, the other one is longitudinal, and then the vertical is Z. And we control motion or forces in 3 translations along those axes and 3 rotations along those axes, and that's where the 6 degrees of freedom come from. The crosshead acts as a plane, as a rigid plane. So if you control the position of one point on the actuator, then you can define any other point in that plane. The motion of the actuator is relative to the reaction floor and the reaction walls. So the crosshead is, as you can see, a very large item, 29 feet roughly end to end. It's a steel box section with internal stiffeners, very large dimensions, 56 inches by 65, and very thick plates, 1.5-inch plates, except for the bottom plate, which is 2 inches thick. It weighs almost 100 kips. All of this was done because we wanted a very stiff member so that it could actually act as a rigid plane under full load, and there's a number of different configurations of actuator loads that we considered. It deflects less than 0.1 inches from one end to the other. The other component, besides the actuators and the crosshead, is the floor in combination with the walls. The floor was also designed to be very stiff under full loading, plus or minus 1/10 of an inch. The floor is 7.5 inches of concrete that's supported on 32 piles that are driven down to bedrock. It is topped with a steel plate of 5.5-inch thickness, and it has a 35-foot by 35-foot plan dimensions. The concrete is post-tensioned in both directions to make it extremely stiff. And there's, in the steel plate, a regular grid of holes that have been drilled and tapped at 18 inches on center. The purpose of the steel plate is to give us a strong, hard bearing surface and also to provide the opportunity to have these drilled and tapped holes so that we can connect directly to the floor instead of having to go down to a layer or a level below the floor like in a traditional lab. Each hole has a capacity of about 125 kips in simultaneous axial loading and shear. The strong walls are L-shaped configuration. They're post-tension to the foundation and they're post-tension to each other. They're 35-foot by 35-foot and 7 feet thick. They also have a series of holes. These are through holes with a 125 kip capacity, simultaneous axial loading and shear. And it was designed so that we could apply the maximum load from the horizontal actuators acting simultaneously. That's like 880 kips at either 16 feet or 32 feet in elevation along the wall. So we have very large out-of-plane moment capacity, very large torsional capacity, and also very stiff. The other component of the mast is what you don't see here is the controller. The controller is a 6-degree of freedom controller that is housed in a computer in the control room that you see there. Let me see if I can get this video going. No, apparently not. But we can control each of the degrees of freedom separately to give us a very wide range of possible motions of the crosshead, therefore possible boundary forces or boundary deformations. The individual degrees of freedom can be, the mode of control can be switched. It can be switched while the specimen is under load. We can slave one degree of freedom to another, and we can have linear combinations of degrees of freedom. So here's a list of some of the features of the controller. I mentioned several of them. In fact, I've probably mentioned all the ones I want to mention here. The last item, the available testing protocol, includes the ramp and hold, where this is done interactively while we're testing. Ramp and hold read from a file, and those two are the traditional methods of quasi-static testing. But we also have the capability for hybrid simulation using ramp and hold, which is the feature of interest here today. Here's an example of how we can use the MAST controller for structural testing. Imagine you had a wall and you wanted to load the wall with a displacement that's applied in the plane of the wall. And so the lateral degree of freedom in the x direction you would control in displacement, and it would be an input command either from a file or done interactively. That's the displacement that you would like to see, or the increment in displacement. In the other horizontal direction, we don't want any loading, so we control in either displacement or force and set that to 0, depending on which of these you prefer. In the vertical direction, we would control it in force if we wanted a constant vertical force or a varying vertical force. And then we have the 3 rotations. The rotation out of plane would be set to 0, either in displacement or force. The rotation in plane would be slaved to the lateral force, because generally, at least under earthquake or wind loading, the moment at the top of the structure is going to be a function of the horizontal force at the top of the structure. And so you apply a displacement at the top, you get a feedback force, and you use that force to calculate the moment input signal. And so that's the kind of capability that the MAST offers you. And then twist about the vertical axis if you want to apply building twist, and you can apply that in force or displacement control, or set it to 0. Some past projects that may be of interest to you. yeah. So the first one is a structural wall. It was built at a medium scale. It's a multi-story wall. This is a project that was led by my colleague, Professor Kathy French, who's the current director of the MAST Laboratory. It involved one of our speakers today, Professor Sri Sridharan from Iowa State University, as well as faculty from the University of Puerto Rico and a practitioner from California. There's a lot that went on in that test, but in terms of the loading scheme, they desired to have a constant axial load, so in the Z direction, they ran it in force control, and the input signal was the force that they wanted. They wanted varying displacements or incremental displacement histories in the two horizontal directions, in the X and the Y. Those are inputs. They also wanted moments at the top of the wall that were proportional to the shear at the top of the wall in the two directions. So as I was discussing previously, you apply a drift in one direction, you get a feedback force, and you use that force to calculate the moment. I think is when I it's just not advancing yet. Could be a file. A second project of interest here is a project that was that involved my colleague Carol Shield, who's also was the director of the MAST Laboratory during the Nice years. She worked with Gustavo Parra of the University of Wisconsin, previously the University of Michigan, and Jerry Lynch from Michigan. They were looking at a flat plate structural system under seismic loading. Of interest here is that they applied biaxial loading history, biaxial displacement history at the top of the specimen, a constant gravity load, but they used the ancillary actuators as supports on the four corners of the slab. The edges of the slab actually represented midpoints of the slab structural system, and then they had ballast loading to simulate gravity load on the slab. Another project involved Jack Maley from Berkeley, Julio Ramirez from Purdue, and Adolfo Matamoros from University of Texas, San Antonio. He was at Kansas at the time of this test. They wanted to simulate constant axial load, varying lateral displacement, but they used the crosshead to provide a fixed condition at the top of the structure. So simply set the rotation to 0 in both directions to simulate that fixed condition. Additionally, they built their specimens at the home institution and just shipped them here. That makes for a much more efficient way of running the mast since you don't have to build on site. Another test of interest was run by Rigoberto Burgueño of Michigan State University and Eric Hines at Tufts. They were looking at structural systems that involve open box concrete structures. These concrete structures are made from concrete panels. They wanted a constant column axial load, but they also wanted a constant moment to shear ratio and a varying lateral displacement in one direction. So, as you can see in the picture, they would apply a displacement at the top of the structure, measure the feedback force, and use that feedback force to calculate the moment such that the moment, the shear, remained constant during the test. Another interesting test was a project run by Roberto Leon of Virginia Tech University and Jerry Hajar at Northeastern. They wanted to test concrete-filled tubes and steel-reinforced concrete beam columns under constant axial load and lateral displacement, but they used the crosshead at the top to simulate a pin condition so that the force was set to 0. So you ended up with a pin at the top. The last test I'll mention here is actually a larger specimen. It's a 2-story, 1 bay by 1 bay steel frame. This project was conducted by Charles Roeder and Don Lehman at the University of Washington, and Taichiro Okazaki used to be here at the University of Minnesota and is now at Hokkaido University in Japan. They wanted to test this steel frame with 2 different types of bracing systems, and so they actually tested it twice. They applied a constant vertical force with a crosshead, 0 top moments by just setting the moment signal to 0 or moment input to 0, and specified biaxial drift. What's of interest here isn't necessarily the loading regime, the loading protocol, but it's that they actually built the structure. The erection of the structure was done using the crosshead as construction equipment, and so avoiding having to use cranes. Okay, very quickly going through some additional features of interest. So we have a data acquisition system. It's a National Instruments data acquisition system, fully integrated in the laboratory, and it's also synchronized with our LED positioning system. It's 16-bit. We have 176 voltage channels, 256 strain channels. We have features in the software that make it quite easy to work with, real-time data archiving, customizable digital display, so what you see during the test in your digital display can be whatever you want, also customizable 2D plots, and all data stored in readable files and text files. We can share screens remotely using WebEx or something similar to that. We also have a variety of instrumentation, you know what that is, LVDTs, string potentiometers, tilt meters, load cells. We have a calibration stand. We also have this LED-based 3D positioning system, the Krypton K600. That's a very valuable piece of equipment. It consists of a unit that has 3 cameras. You use LED targets. You place them on the structure at different locations. You run the strobe so that the LEDs emit a signal that the camera picks up. Since you have 3 cameras, you can use triangulation to determine the position, and then this is stored in the computer. You can use this to determine position, but you can also use it to determine unit strains on a structure. Another nice feature of the MAST laboratory is how the instrumentation plan was set up. So from the instrument, we go directly to connection boxes, which are available in the payload area. These connection boxes are connected with cables that go to trench cables, and so there are trenches around. You can see the shaded area of the trenches around the lab floor, and then the cables in the trenches go directly to the data acquisition system that's housed in the control room where the controller is. That way we can keep the amount of cabling on the payload area to a minimum. And then we also have imaging equipment besides the Krypton. We have 4 towers. The towers have the equipment that you see on the left. There is a light, there's a camera, and they're on a platform. The platform and the cameras are computer controlled from the control room. The lights themselves you have to run manually. So now I'd like to show some videos of past projects, assuming if we're doing well on time. Okay. So the first video is just a movement of the crosshead by different directions with the control system and with the actuators to give you an idea of the range of movement. This is one of the things I wanted to show you with that video earlier. You can see a lot better here. And so you get essentially whatever you want as far as movement is concerned. Here we have an individual steel. This is the concrete-filled tube, and you can see the range of motions it was going through. You can also see where the steel tube is buckling at the base of the specimen. Here you see a precast concrete shear wall. This is a project conducted by Sri Sridharan from Iowa State, who's going to be our speaker later on, and Kathy French. You can see the range of motion. One of the things that the MAST allows us to do is, besides very large forces, are very large drifts. And so for full-scale structural components or systems, it's been difficult in the past to be able to push the system to drifts or displacements that characterize the full range of response of the system. So we may know what happens up to a certain point, but after that, you read a lot of research papers, basically the researchers indicate that they were out of stroke, that's as far as they could go with their equipment. Well, that's certainly not as common with equipment like this. As you can see, we work very fast here. We run around the specimens. Okay. How do I skip over? Okay, this is the T-wall. This specimen was built in the MAST lab and then rolled into place into the payload area. Oh, you built inside, okay. For the specimen as large as this one, the lateral displacements at the top can be extremely large, and with traditional quasi-static loading equipment, it may be difficult to accommodate that. That was one of the goals that we had when we designed this. Now, all of these have been quasi-static tests, and I want you to think about the jump that we would have to make to go from this to hybrid simulation. We have really most of the features that we need except for the control algorithms for hybrid simulation. We now have those in place thanks to our good friends at MTS, and they'll be talking more about that later on. This is the flat plate structure. You can see the construction going on. It was built in this end of the lab. This one was rolled into place. To roll it into place, one of the actuators has to come down. It's the only unfortunate aspect, and it is a major operation. But once that is removed, then the specimen is rolled into place. The actuator is replaced. And here you see the test. Here's a specimen that was shipped to us, and some components were built here. As you can see, there's some base blocks, but building these smaller base blocks is a lot easier than building the whole thing here. Quite often we find that when we start in one specimen can be improved, the construction and erection process, and we may make modifications for the next one. Now, notice that top block, it's not square with the rest of the specimen. It's at a 45-degree angle. And the reason is that this specimen is very long. In order to get it into the payload area, it was actually placed diagonally. That's possible because the controller for the MAST allows the user to define coordinate systems as long as it's orthogonal, define a coordinate system however they want. The other nice feature is that you specify the command signals in terms of that coordinate system, and all of the projections onto the displaced current coordinate system is done internally by the controller. And you can see that specimen has been placed diagonally so that it fits. Otherwise, it would have interfered with the two of the vertical actuators. Rather involved test, as you can see. You also notice that the specimen was actually picked up by the mast so that the bottom pin could be installed. Quite often what dictates, to a great extent, how long it takes to test in the mast is not only the building process and direction of the specimen, but also the amount of instrumentation and when and how quickly it is installed. So I'm going to move on. It's another one of these. Sorry? This is a similar test setup, but it's with a steel beam column frame. This is the actual test. It was placed diagonally once again for the same reason, so that a longer specimen could fit in place. And this gives you a great idea of the amount of displacement that can be imposed by the mast system. This is a steel truss system, so-called staggered truss building system. Very flexible, so you can see, once again, what you can do with the mast with these very flexible large-scale or full-scale components. This is a very large concrete column. The idea was to get an idea if the size has an impact on the performance, because it's about twice as big as most of the other column tests have been done previous to that. And also what happens when you push the specimen to very large displacements. It also had an imaging system that was used. You can see the imaging system being placed at times to get an indication of how much damage there is at cross sections near the base. Okay. This is the steel frame. Maybe we'll look at the erection that used the mast. So it could have been very complicated because of the size of the specimen, and the requirements to erect all of those pieces became a little easier. The welding that was done, more system. This is the last one, Paul. And this is the test of that system. This is the diagonal brace system with very flexible braces and very flexible gusset plates. You can see the amount of movement that the diagonals went through, but for design type motions, it actually performed very well. Had the gusset plates been stiffer, then the performance wouldn't have been nearly as good.